Okay, let's begin part one of the lecture, which is about model specification. And the first topic we're going to look at is data transformations. Now, in this part of the lecture, I want to talk about transformations that we can apply to data in order to better meet the assumptions that govern the statistical models we're trying to estimate. And we can apply transformations to the dependent variable, to the independent variable, or to both. And by transformations, we simply mean applying some function to those variables. That could be the square root, it could be the log, it could be reciprocal, or it could be a power. And we're first going to consider transformations that are made to achieve three specific objectives: to stabilize the variance of the variable, to normalize the data, or to address nonlinearities and generalize model specification. Now, an important point: transforming either the independent variable or the response can help with this third objective. That is, it can help linearization, it can help ensure the regression function falls within the linear and parameters framework. But if we want to achieve either the first or second objective, stabilize the variance or normalize the data, then only a transformation of the response will do that. So if we're worried about non-constant error variance or about errors that are not normally distributed, we have to look at a transformation of the response. Now, I've included some theory, and I've called this an excursus because it's not essential for the course, but I've put it here for those of you who want some background mathematical detail on how the transformation of a random variable relates to the mathematical properties of distributions, if you like. As I say, not essential, but for some of you, it will give you a solid understanding of what a transformation is. So we've simply got three slides, and let me just take you through at a high level what these are saying so that you understand the main idea. First of all, we define what a transformation is, and a transformation is simply applying a function to a random variable. As I said previously, that could be something like a square root, a logarithm, a reciprocal, or a power. Then we have two theorems that talk about what is the distribution of the transformed random variable. And basically what this slide is saying is it's saying that if we know the distribution of our original variable x, then under suitable conditions we can actually derive the distribution of our transformed variable y. For one-to-one monotonic transformations, and that's the examples given here, this is simply done using the inverse transformation and the chain rule. More complicated transformations, such as squaring a variable, require us to account for multiple values of x mapping to the same value of y. And one of the main results from these slides that I want you to take away and that we're going to use later is that if x is log normally distributed, then the log of x is going to be normally distributed. And that's one of the reasons why logarithmic transformations are so widely used in statistics. They often produce variables that are much closer to normality, making standard statistical methods more appropriate. And that specific example is given here. But let me move on to the practical use of transformations, and we're going to go through each objective. And as I said, the first objective of a transformation is to stabilize variance. As we said in our previous lectures, in order for least squares estimation to be blue, the variance must be constant, and we proved that in lectures 4 and 5. But response variables often follow probability distributions in which the variance is functionally related to the mean, as shown here. So the variance of y is sigma squared times some function v of the mean mu y. So it doesn't have this nice property here, but it's just a constant term. It's a constant term times some function of the mean. And the question is, what can we do when this happens? So to address this, we're going to introduce a transformation, and the transformation we're going to call z. It's the g of y, and we can take an approximation to this transformation, a first order Taylor approximation, which would have this form here. Now, for this first order Taylor approximation, this gives an expected value of z equal to the g of mu y, and it gives the variance of z equal to sigma squared times v of mu y times the first derivative of g of the at the mean squared. So that is the expectation of our transformed random variable. That's the variance. Now, we suspect the variance has this form here. Our transformed random variable, so the variance we suspect has two terms. It's got sigma squared y times v of the mu of y. And under our transformation, the variance is going to have three terms. Sigma squared y, v mu of y, and then this term here, the derivative at the point of mu y squared. And what we want to do is get these two terms to cancel out. That's the idea. So in other words, we can break the dependence between the mean and the variance if we choose our transformation so that its derivative is directly proportional to v to the power minus 1/2. That is, if g is proportional to the integral of v of y to the minus 1/2, then these two terms are going to cancel, and we're going to get a variance of z that is equal to sigma squared y. It's going to give us constant variance. And we'll look at these in the tutorial actually, but some standard cases are listed here in the slide. If the variance is proportional directly to the mean, then the square root transformation is going to stabilize variance, and you can show that just by working through these calculations given here. If the variance is proportional to the mean, then we can use the log, and that's going to do the trick. It's going to cancel these two terms. If the variance is proportional to the mean cubed, then 1 over root y is going to do the trick. And if it's proportional to the mean to the 4th power, then the reciprocal 1 over y is going to break the dependence and give us constant variance. So, if we have reason to believe that the mean variance relationship takes one of these forms, then we know which transformation will break the dependence. The difficulty in practice, of course, is that we often don't know the mean variance relationship, and that limits the applicability of the transformation approach to stabilize variance. And that's why generalized linear models that we're going to look at in lecture 7 are often a better example. But these transformations are still used, they are still important, and we're going to work through some examples of this in the tutorial. Okay, let's move on to the second reason why we might want to transform random variables, and that is to satisfy the condition of normality. Now remember that our null normality is not a specific Gauss-Markov condition. We assume normality of the errors in order to do exact inference. So the t-test, the f-tests, the standard errors, and the confidence intervals, calculation of confidence intervals, all rely on the assumption of normality. Now, a transformation of the dependent variable can help us meet this assumption of normality. And such transformations tend to be effective when the distribution of the residuals is skewed, but less effective when they are symmetric but non-normal. For example, for positive data that exhibit a skew, a log transformation can help in achieving symmetry and normality, and that's exactly the result we noted a moment ago, where a log transformation takes a log normal distribution to a normal one. So that's shown in the excursus slides for those of you who want a bit more depth on this. So a log transformation is one transformation we can apply to achieve normality. Another common and flexible approach is called the Box-Cox family of transformations governed by a parameter called lambda, and that's the equations shown here. When lambda is not equal to 0, the transformation is y to lambda minus 1 divided by lambda, and when lambda equals 0, the transformation is simply the log transformation. So the assumed model is that the transformed response is normal with mean x transpose beta and variance sigma squared, and the transformation induces symmetry, normality in the distribution of y. Relative to other transformations, the advantages of this Box-Cox transformation are that the lambda that best fits the data can be chosen actually by maximum likelihood estimation, so we can choose it optimally, and the function g lambda is continuous and infinitely differentiable at lambda equals 0. So let's look at a specific application of these two transformations to show how they work. And we're going to look at the London Underground journey time data, again, introduced in previous lectures. So the figure shows histograms of the journey time variable, that is the y variable, its log transformation and its Box-Cox transformation. And what you can see is that the original data exhibit clear right-hand skew. This is very common in travel time data, so we get some very big values. The skewness statistic is around 1, indicating strong right-hand skew. But look at the transformed data. The transformed data look much more normal. And actually, both of these transformations are effective in approximately normalizing the data. We can see that visually because we have more symmetric bell-shaped distributions, and the skewness statistics confirm this. So we have minor left skew of minus 0.167 under the log transformation and minus 0.008 for the Box-Cox transformation. So using this principle, what we're now going to do is we're going to estimate our multiple linear regression model using the transformed data as the dependent variable rather than untransformed, and we're going to look at the distribution of the residuals. And the figure below shows histograms of the residuals from 3 multiple linear regression models using the original untransformed journey time, using the log transformed journey time, and using the Box-Cox transformed journey time. And what you can see is that the residuals from the untransformed model are clearly not normally distributed. And this would be a diagnostic we want to look at in any regression model. We should always study the distribution of the residuals and see if they're approximately satisfying the condition of normality. But here we can see a pronounced skew. However, both the log transformed and the Box-Cox transformation are effective in normalizing the residuals. You can see we get these very nice, symmetric, normal-looking Gaussian distributions. The Box-Cox version in particular looks very close to a normal distribution. And this matters because, as I said, if we use the assumption of normality for inference, then we've got to get this right. So if our standard errors, our t-statistics, our confidence intervals, and our rest tests were based on this untransformed model, the normality assumption is violated and we cannot rely on the inference we're getting from that model. So based on either of the transformed models, we can be much more confident that the assumption of normality is holding. Okay, now let's talk about transformations and model functional form. And I want to say at the start that an important property of transformations that you must understand, actually as we noted in lecture 4, is that a transformation alters the model's assumed mathematical form, its underlying mathematical form. So for instance, if we propose the model for estimation with log journey time as the response, so not journey time itself, but the log, then the mathematical form we're assuming is as follows. We're assuming that the journey time is equal to e to the power of beta naught plus beta 1. So in other words, we end up with the right-hand side being exponential if we log gt. That's the mathematical form we're assuming. That's called a semi-log mathematical form. So journey time equals the exponent of the whole of the right-hand side. Or if we were to propose the model that was logging both sides, so log-log model, log y regressed on the logs of the x variables, then we're explicitly assuming a multiplicative functional form. That is to say, we're assuming this form here, in which y equals e to the beta naught times the product of the x's, each raised to the power of beta, times the error term, times e to the power of the error term. So the point is that the parameters from transform models must be interpreted in light of the corresponding mathematical form that we're assuming underpinning all of this. And to illustrate this, we're going to look at the interpretation of log transform models, which are used very commonly. So let's start by looking at a model in which we've simply transformed the response variable. The betas in such a model can be written in this form here. So the partial derivative of the expectation of log y given x with respect to xj, we can take the log outside of the expectation, which is valid provided the error term is independent of x, and then simply using the rules of differentiation for the logarithm, we can see that this equals the partial derivative of the regression function with respect to xj divided by the regression function itself. So these two expressions there. Or in other words, each beta j measures the marginal proportional change in the conditional expectation of the response for a unit change in xj. So the interpretation of beta has changed. In an untransformed model, beta j is simply telling us the absolute change in the expected response for a unit change in the covariates. But with a log transform model, log of the response, it tells us the proportional change. Second, let's look at a model in which we have logged both the response and the covariates, so a log-log model. The beta j's can now be written as the derivative of the log of the expected y with respect to log xj. And working through this gives us this expression here, the proportional change in the expected response divided by the proportional change in xj. And those of you who have studied economics will be very familiar with this. Coefficients of this kind are referred to as elasticities, or in this case partial elasticities, because we're using the partial derivative. And they measure the proportional change in conditional expectation of the response for a proportional change in xj, and therefore everything becomes unit-free and proportional and delivers a much easier interpretation. So that's the point about an elasticity. Now let me try and make this concrete with two simple examples. First, we're going to look at the semi-log model. The log of y has been regressed on x. A 1 unit increase in x is associated with approximately 100 times beta 1% change in the expected value of y. So in the journey time example on the slide, if the log of journey time equals 1.9 plus 0.10 times distance, then an additional 1 kilometre of journey time increases expected journey time by approximately 10%. In the log-log model, log of y regressed on the log of x, the coefficient beta 1 is now, as we said, an elasticity. It's telling us how a 1% increase in y is associated with an approximate beta 1% increase in the expected value of y. So if beta 1 is 0.55, then a 10% increase in journey time is associated with an approximate 5.5% increase in expected journey time. So the key point to take away then is a log transformation changes the interpretation of the coefficients from changes in units to changes in percentages. Okay, and then thirdly, I want to talk about transformations that seek to address non-linearities in the data. Now we said in weeks 3 and 4 that the multiple linear regression model is constrained to be linear in the parameters, so y equals x beta plus var epsilon. But within that linear and parameters framework, we have considerable freedom to choose the specific functional form of the model. Now typically, we don't know what the true functional form is, and we're going to use scientific knowledge and empirical approximation to postulate a form for estimation. In lecture 4, we considered transformations that linearize nonlinear models, and we also noted that a second-order response surface, shown here with squared terms and cross-product terms, as justified by Taylor theorem, can provide a quite general approximation to an unknown, potentially nonlinear functional form. I now want to cover briefly two additional techniques that are used routinely in practice to improve model approximation and to relax the additivity assumption, and that is I'm going to look at interaction terms and we're going to look at dummy variables. So let's start with interaction terms. Consider a multiple linear regression model with two explanatory variables. So y equals beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. The model is said to be additive because the effects of x1 and x2 on the expected response are simply added together to obtain their joint effect. And additivity, of course, implies the effect of x1 on the expected response is always beta 1, regardless of the value x2 takes, and vice versa. Now that additivity assumption may not hold. When two covariates do not act additively on the mean response, we say that there is an interaction between them, and interactions can be accommodated by including a third predictor, an interaction term, which is simply the product of the two variables, beta 3 times x1 times x2. And with the interaction term in the model, if we take partial derivatives, then we can see that the partial effect of x1 is beta 1 plus beta 3 times x2. And the partial effect of x2 is now beta 2 plus beta 3 times x1. So that each variable's effect now depends on the value that the other variable takes, which is exactly what we mean by an interaction. So let's look at an example of where an interaction could be useful, and we're going to use the London Underground journey time data. So we're going to estimate our journey time model with an interaction between headway and distance shown here, and beta 5 corresponding to the coefficient in this interaction. And the logic we're using here is that headway directly affects waiting times at the origin station. That's the main effect, beta 1. But it also influences dwell times at other stations along the route, and that effect should grow with distance, and that's the interaction term. So here we have our results. This is the result on the interaction term. The coefficient on headway is 0.034. And the coefficient on the interaction between headway and distance is minus 0.05 approximately. So what this is telling us is that a 1 minute increase in headway increases expected journey time proportionally by 0.034 minus 0.05 times distance. Note the response is logged, so these are proportional effects as we discussed a moment ago. So hence, the further we travel, the more impact headway has, and that seems reasonable. Now note that the p-value on the interaction is very small, indicating strong evidence against the null that beta 5 is 0, so there is strong evidence of an interaction here. That's just one example of where an interaction matters and where it's really telling us something that's important about the data and about the effect of headway on journey times. One further point, notice that the hierarchy principle requires that the main effect be included in the model alongside their interactions, even if the main effect appears insignificant. So in practice, always do that. If you include headway times distance, you must keep headway and distance in the model. That's the idea of the hierarchy principle. Okay, so that's the idea of interaction variables. They're simply mean that as I said previously, the effect of a variable on the response can depend on other variables. We're now going to look at dummy variables, also called indicator variables, which are a useful device in multiple linear regression modeling for representing qualitative or unmeasured covariates. So a dummy variable is a binary variable. It takes the value of 0 or 1. Taking the value of 1 for observations where some effect is present, or the value of 0 where it's not, or where the observation belongs to some group and 0 otherwise. Now, dummies offer a convenient way of building discrete shifts into the regression function, and there are two kinds of shifts that we can look at, an intercept shift and a slope shift, and we'll now just talk about each of these. So let's look first at intercept shift. Let D be a dummy variable indicating membership of some group G. Adding D to the simple linear regression gives the model on the slide shown here. So for units in the group, the intercept is beta 0 plus beta 1. For units that are not in the group, it's simply beta 0. So as long as beta 1 is non-zero, the group has its own intercept, and the coefficient on the dummy variable beta 1 represents the average difference in the response between the units in the group and the units outside the group. So it's simply shifting the intercept for observations that are defined within some group. The second type of dummy variable we can look at is one in which it actually shifts the slope, which we get by interacting the dummy variables with a covariate x. Now for units in the group, the slope of the regression line is beta 1 plus beta 2, shown here, while for units outside the group, the slope is simply beta 1. So this is the shift to use when we believe that the marginal effects in the regression differ of course groups. And of course we can include both. We can include a dummy variable on its own and a dummy interacted with x to allow both intercept and slopes to differ across groups. Now that's just shown two groups. The extension to multiple categories is straightforward. With G categories, we create G-1 dummy variables, and that brings us to what's called the dummy variable trap, which is important in practice to always remember. As long as you include an overall intercept in the model, only ever introduce G-1 dummies to the model. If you introduced all G dummies, then all dummies would sum to 1 at every observation, exactly reproducing the constant term, giving perfect multicollinearity, and that would mean the model would not be able to be estimated. So when you introduce dummy variables, as long as you include an intercept, you must drop dummies for one of the categories, and that then becomes the reference that the intercept takes. It takes the value of the dummy variable for the category that you have dropped. So let's look at an example. We're going to estimate the London Underground journey time model again, but this time with dummy variables. And we're going to include dummy variables representing each London Underground line. This is just an intercept shift, and we're going to use this intercept shift to capture the influence of line-specific facts, features and technologies, so differences in signalling systems, in rolling stock, in network technology and so on, that we believe influence journey time, but we haven't measured them directly. So we're not able to measure them, but we're going to put dummy variables into the model to shift the intercept to account for them. And looking at the results, this is the results on the dummy variables here. What we can see is that the line dummy variables all have large T statistics and very small p-values. So this gives us strong evidence that there are in fact line-specific effects. For example, the coefficient of about -2 on one of the lines says that the journey times on that line are around 20% lower, other things equal, than on the reference line, which is the line that we've omitted. So, finally, note that if we want to test the joint hypothesis that all the line effects are zero, we can use an F-test comparing the model without the dummies, what we call the restricted model, against the model that's got the dummies included, the unrestricted model, exactly as we did in lecture 5. So that's the principle of dummy variables. Dummy variables are there to account for differences within defined groups that we have within the data. To do this either by shifting the intercept, so allow these defined groups to have a different intercept, or actually allowing them to have different marginal effects by allowing the dummies to shift the slope.